and start share screen. In the usual way here. All right. Apple makes everything so easy, they claim. I don't always think so. Let's see here. Let me get this focused here. Okay. Yeah. So we finished up in the middle of some rather lengthy stuff. So I'm going to try to review some of it before we get started with the real lecture tonight. So the summary is we're dealing with, in the first place, a lot of orbitals. Orbitals are a product of a spatial times the spin part, and the spatial part is the variational parameters of the variational method that we're using in Hartree-Fock theory. The spin part is plus and minus a half, which is assigned to the orbitals before we start. After some rigmarole, we come to the Hartree-Fock equations, which are summarized here. It has the form of a single particle Schrodinger-like operator acting on the orbital gives you an energy eigenvalue times that orbital. This is, I call it a pseudo energy eigenvalue because it's not a real energy of the system. It has its origin as a Lagrange multiplier in the variational method. The direct and exchange potentials which appear here, it's assumed that they've been averaged over both angles and spin so that the operator in the parentheses is a central force Hamiltonian. And the result is that the lambda, which is the designator for the orbital itself, can be identified with the central field quantum numbers of the solution for this single particle Hamiltonian. The trial wave function itself is a Slater determinant, which is composed of the orbitals. Last time in the last lecture, we were working on a new project, which was to improve on the Hartree-Fock method. That's to say, as described up to this point. The main drawback with the method as described up to this point is that the Slater determinant, the trial wave function, is not an eigenfunction of the exact quantum numbers of the system. In particular, it is in fact an eigenfunction of the operators L sub z, S sub z, and parity, but not of the operators L squared and S squared. And we know, since we're trying to solve the electrostatic model, we know that those are good quantum numbers of they're exact quantum numbers of the energy eigenstates. So there's no approximation in that. So what we'd like to be able to do is to identify the numbers, identify the states by their exact quantum numbers. So to do that, we notice that the Slater determinant, which began as life as a trial wave function, is actually an eigenfunction of a certain Hamiltonian, which I call H naught. And that Hamiltonian is just the sum of these single particle Hamiltonians that appear up here in the Hartree-Fock theory, just summed over all the electrons. So it's a sum of single particle Hamiltonians. This is called the central field approximation, and it's more crude approximation than the electrostatic model. The energy E0 that appears here is a sum of the pseudo energies in the Hartree-Fock theory. The epsilon lambdas up here, otherwise the Lagrange multipliers. All right, so what's that good for? Well, what's that good for is the following: is that this H naught is not the Hamiltonian we want to solve. We want to solve the electrostatic model. But the way we do it is we write this as we fix this up so that we add a term as a perturbation to H0, which creates the electrostatic model. So what we really want to solve is H phi equals E phi, where the H has two terms, H0 and H1. I'll come to H2 in a moment, where H0 is this H0 that you see up above here. And the H1 is the exact inter-electron interaction minus the direct minus exchange potentials. So adding H0 and H1, this H0 and this H1 gives you the electrostatic model, because these Hartree-Fock self-consistent potentials cancel out, and you're just left with the inter-electron potential. The point being that this H1, which is sometimes called the residual Coulomb interaction, the idea is that it's the two particle Coulomb interaction amongst the electrons with a kind of a rotational average subtracted off. So that's why it's called residual Coulomb. In any case, this is much smaller than just the first term alone. And so it's suitable for using perturbation theory. The H2 is the spin orbit interactions, which we add in here as a sample of the fine structure corrections, which involves even further higher order corrections beyond the H1. So by treating H0 plus H1 by perturbation theory, we're in a position to get more accurate eigenstates than a single Slater determinant, and also, as it turns out, to get eigenstates which are simultaneously eigenstates of the good quantum numbers of the system. So that's, I hope not, that's part of a review of where we left off last time, but I'm not done yet. Let me continue. I have a page here summarizing the potentials. Maybe I shouldn't spend any time on this because I've been over it before, but these are the direct and exchange potentials. They're self-consistent, that is to say they're expressed in terms of the orbitals u mu here. And then the averaging is described very roughly down here. Basically, we average over angles for the direct potential to make the direct potential a function of radius only and not of the direction of the R vector. And we do something similar but more complicated for the exchange potential, more complicated because it's really an integral transform and not a multiplicative operator. We also average the exchange potential over spins, which makes the Hamiltonian independent of spin, and therefore it gives it the form of a central force Hamiltonian. Anyway, those are the potentials. In any case, to continue with what we're going to do with this, we need to study the unperturbed. Before we can do perturbation theory on our H0 plus H1, we need to look at the degeneracies, the eigenstates, degeneracies, and so on of H0. So this phi 0 was an eigenstate of H0. That is to say, it's a single Slater determinant written down an earlier page. A better notation for this is to write it in terms of two things. First of all, an electron configuration. What an electron configuration is, so to back up a little bit, the Slater determinant is made up of single particle orbitals, and it's specified by the list of orbitals that are occupied. And since those are now central force orbitals, that amounts to a list of central force quantum numbers which are occupied. So part of the information about that is containing the electron configuration, because what it does is it tells you how many electrons there are in each subshell. So for example, with carbon, 1s squared, 2s squared, 2p squared means that the 1s and 2s subshells have 2 electrons in them, which means that they're filled. The filled subshell is otherwise known as a complete subshell. And the 2p subshell has only 2 electrons out of 6 slots, so it's only partially filled. That's called an incomplete subshell. In any case, that's the information conveyed by the electron configuration. Now, the magnetic quantum numbers, so the electron configuration gives you the N and L quantum numbers, you see, of the electrons. As far as the magnetic quantum numbers are concerned, that's the M sub L and M sub S. There's only one way to assign them for complete subshells. In this case, carbon would be the 1s squared and 2s squared. They're filled, so all the magnetic quantum numbers are used up. But in the incomplete subshell, we need to give a list of the magnetic quantum numbers of the occupied subshells. This is what we call an M set. So the complete set of orbitals that go into a Slater determinant is specified first by the configuration and secondly by the M set, where the M set is the ML and MS quantum numbers for electrons in incomplete subshells. All you need to do is just list the quantum numbers. You don't need to specify an ordering of them, because changing the order, at most that it does is change the sign of the Slater determinant and doesn't give you a physically distinct state. It's only the occupied orbitals that matter. So in the case of carbon, the 2p subshell has 6 slots. It's 2 times 2l plus 1 is 6. And so the number of M sets, since there are 2 electrons to go in there, is the binomial coefficient 6 choose 2, which is equal to 15. That means there's 15 different ways of assigning M sets for the ground state of the central field approximation to carbon, and therefore that ground state is 15-fold degenerate. So that means that when we're going to have to do degenerate perturbation theory, or think about it anyway, in studying that perturbation H1, which was the residual Coulomb interaction. So this is kind of the setup then. Here's a list of the good quantum numbers of the electrostatic model. It's L squared, LZ, S squared, SC, and pi. Those are the operators. The quantum numbers themselves are denoted by L, capital letters all across, L, M sub L, S, and M sub S in parity pi. A single Slater determinant is automatically an eigenstate of LZ, S sub Z, and parity pi. In fact, the parity depends only on the electron configuration. So we're going to be working within just a single electron configuration. For example, for carbon, it's even. It's plus one parity. So the main interest is on the L squared and S squared. We'd like to get eigenstates of them as well. So this is going to require us to form linear combinations of in the case of carbon, for example, linear combinations of the 15 Slater determinants to make eigenstates of both L squared and S squared. All right, now I think that takes us up to where we left off last time. Are there any questions about that? Any questions about that before we proceed? So that took me into some real time here. If there are no questions, I'm going to put this on hold because I want to address a question that was raised in an email from a student. And it's an important thing to think through. And it's the kind of thing that if you're thinking carefully about this business, you should think about. So the question was this: is in these manipulations in Hartree-Fock theory, we're using Lagrange multipliers to impose a constraint that the wave function should be normalized. And that's essential to get the Schrodinger-like form for the ultimate wave equation. You get the same thing was true in the Hartree theory. We had a Lagrange multiplier to normalize the wave functions. So now in the actual manipulations that we carried out in evaluating the integrals, we used the fact that the wave functions were normalized, and then we used that to put together the final functional for which was to be varied for the Hartree-Fock theory. Now the question was raised as to why is it legitimate to introduce the constraint into the functional before we've carried out the variations, as I say, before we've carried out the derivatives or the functional derivatives. Doesn't that lead to a mistake, or could that lead to a mistake? And the answer is no. The way that we're doing it is actually okay. And I'll give you an example here to explain to you why that's so. Let's suppose I have a function in 3 variables, x, y, and z. And let's say that function is equal to r squared minus x, let's say, where r squared is the obvious meaning of x squared plus y squared plus z squared. And I want to minimize this function or maximize it subject to the constraint that we want to look at the function only on the surface of the sphere r squared equals 1. Okay? So the Lagrange multiplier way of doing this would be introduce a new function, let me call it capital F, which is a function of x, y, and z, and it also depends on the Lagrange multiplier lambda. And it's the old function, which is r squared minus x. And then we have, or let's make it with a minus sign, we have lambda of r squared minus 1. So r squared minus 1, you see, is the constraint. By varying lambda, you get the condition r squared equals 1, and that's the constraint surface we want to look at. So I want to so get the idea. There's this function which is defined in all of 3-dimensional space. I won't draw the picture, but there's a sphere there, and we're only interested in finding the minimum or maximum on the surface of the sphere. All right. Now then, what I'm going to do is take this r squared here, and I'm going to replace it by 1. Why not? Because the constraint is going to force r squared to equal to 1, right? So why can't I just go ahead and put it in here like that, set that equal to 1? The answer is I can do that. And that's what we're doing here in this in the analog of that in our Hartree-Fock calculations. But the question is, why does it work? If I replace this r squared by 1, then I'm changing the value of the function capital F, or if you like, it's the function lowercase f, which is the original function we were talking about. It's no longer the same function. It's 1 minus x instead of r squared minus x. And so out in 3-dimensional space, those functions aren't the same. However, on the constraint manifold, they are the same. And what the Lagrange multiplier method is, so what you might say is that the upper leaving it as r squared, you might call that the honest way of doing this problem. Replacing the r squared by minus 1, is that a cheat? That's the question. The answer is it's not a cheat, but here's why. The reason is that no matter which of these two ways I do it, I'm going to come up with the minimum, or really the critical point, of the function f on the surface of the sphere. And making this change does not change the values of the function on that surface of the sphere. On the constraint surface, the values of the function have not changed. And therefore, the maximum, minimum, saddle points, and so on haven't changed either. They've changed out in the rest of the three dimensionals, in the ambient space, they've changed there. And you will find the Lagrange multiplier also changes. But the points on the constraint surface where the maximum minimum are and the values of those maximum and minimum haven't changed at all. This is actually an interesting example to go through, because if you do the algebra, what you find is that, you know, it's at the antipodes of the sphere where x equals plus and minus 1. Of course, that's where x is maximum or minimum, as you can see easily geometrically, but it gives you the right answer. But you can try this both ways and see what comes out. You'll also see, if you do that, that the Lagrange multiplier actually does change. Okay, I hope that helps clarify that. Are there any questions about that? I think the question came up originally because somebody had learned that in the case of Lagrangian mechanics, you've got to be careful about taking the equations of motion and plugging them back into the Lagrangian. And it's true, you have to do that. You can get into trouble if you do that in the wrong way. But what we're doing here is actually okay. If you want to address, if you want me to address, you know, the difficulties or what you need to be careful about with the Lagrangians, that's a different topic, and we could talk about that separately. But for our problem here, this is how this works out. Okay. The method of Lagrange multipliers, I think, is almost never explained anywhere. I don't know where it's explained. And in the places where it is explained, I'll bet it's not done very well. I don't know where you're supposed to learn this. I should write some notes on it someday. It's a mathematical technique that one could talk about. It's best understood actually in terms of differential forms, but you can explain it without going into that. All right, then with that digression, I want to go back to Hartree-Fock and the perturbation analysis of correcting things for getting the exact quantum numbers we want. So here's the last page that I had up on the screen here, which shows you the list of good quantum numbers. So thinking of the case of carbon, for example, we have this 15-dimensional ground eigenspace of the central field Hamiltonian H0. And if we add H1, which is residual Coulomb interaction to it, we'll get the electrostatic model. So let's keep that in mind. Now then, the basis vectors of this 15-dimensional space, at least they start out this way, are the 15 Slater determinants we get by distributing those two electrons among the six empty orbitals. So that's what they are. They just differ by the orbitals they're in. Most of the orbitals will be the same. All the core orbitals are the same for all of the Slater determinants. It's just the last two for the incomplete subshell that get distributed in different ways. Anyway, that's what they are. By the way, we in the last lecture we went through a detailed enumeration of what those M sets are for the case of carbon. Here they are listed 1 through 15. Here's the two ML1, ML2, the two orbital magnetic quantum numbers, and MS1 and MS2, the two spin quantum numbers. And I went through the construction of this table. And if you're careful how you do it, you get you should get the right answer, which is given by 15, the binomial coefficient. 6 choose 2. I'll come back to this table in a minute, but that's just a detailed enumeration of those. So each entry in this table, understand, represents a different Slater determinant. That's the idea. Okay. Now then, so what we could do to do the perturbation theory for the H1 is, it's going to be degenerate perturbation theory. We could do this. We could do the M sets. Or maybe back up just a little bit. The Slater determinants that I'm calling phi 0 here don't actually give enough information. If I were to change the notation and write it as configuration semicolon M set, that would be a complete specification of the Slater determinant, because the configuration gives the N and L quantum numbers and the M set gives the magnetic quantum numbers. If the configuration is understood, which it is for the case of carbon here, we could even suppress that and just talk about M sets. So suppose we do that. Then what we've got is we've got, to do the perturbation theory, we need to consider matrix elements like this, where we've got M sets on one side and primed M sets on the other side. You'd have a 15 by 15 matrix here of H1, and you'd need to diagonalize that to find the energy shifts. Well, it's much better, instead of using MSETs, to use eigenstates of the operators L squared, S squared, LZ, and S sub Z, which I'll represent by their quantum numbers here. And these are going to be linear combinations of the Slater determinants with MSET. So the linear can, there's sums over the MSETs of coefficients like this. Let's spell coefficient right, coefficients of coefficients multiplied times the MSETs. That's to say we form linear combinations of these 15 Slater determinants to make eigenstates of L squared and L squared and S squared. These things are already eigenstates of ML and MS, but we want to make them also eigenstates of L squared and S squared with quantum numbers L and S. Now, the reason for doing that is that the operators L squared, S squared, LZ, and S sub Z, which are the operators corresponding to those four quantum numbers, they all commute with H1. And so the matrix elements of H1 in the new basis, which look like this, LS, ML, and MS, sandwiched around H1, in this basis, the matrix elements are diagonal. I don't need any primes on the, I mean, naively, you might think you need primes in all four variables because those are the labels of the basis vectors in the unperturbed eigenspace. But because H1 commutes with all four of the operators, of which these are the quantum numbers, you don't actually need the primes. And thus the energy shifts are diagonal. And so once again, we get away without having to diagonalize matrices and doing a degenerate perturbation theory. And as far as the energy shifts themselves, let's call them delta E. What do they depend on? They depend on L and S, but they don't depend on the magnetic quantum numbers because of rotational invariance, the Wigner-Eckhart theorem, the fact that this is a scalar operator. H1 is a scalar operator. It's a scalar operator not only under orbital rotations, but also under spin rotations. That's what we got by doing the averaging of the direct and exchange potentials. We made it that way. But the result is that it commutes with all three components of the orbital angular momentum as well as the spin angular momentum, both. And therefore, with the operators L squared and LZ and S squared and SC, which are functions of those, and thus it's diagonal in all four of those quantum numbers. And so the energy shifts are just the diagonal elements. They don't depend on the magnetic quantum numbers. They therefore depend on L and S. And what this means is this common energy E. So the total energy is going to be then E0 plus this delta ELS, you see. Here, let me write it right. It's going to be, let me get some space here so you can see it better. It's going to be the E0 is the unperturbed energy, and then we add the delta E sub LS. And the result is the energy levels will now depend on L and S. This is what we expect. The L and S give you the symmetry classes of the electrostatic model, and the different energies in different symmetry classes are not likely to be the same. So what this is going to do, in other words, is going to give us a way of identifying the low-lying levels of the multi-electron atom, including their exact quantum numbers. And I think this can be regarded as kind of the basic level of basic understanding of the structure of multi-electron atoms, which is why I'm going through this. All right, so we want to find this delta E sub LS. Well, how would we do that? Well, the first thing you need to do is to determine which L and S values occur inside the eigenspace of the ground state. In this case, this 15-dimensional space. Which L and S values are there? That's the first question. This is analogous to adding two angular momenta, 1 and 3/2, and asking which total angular momenta come out. You know the rules for that. It ranges between the maximum and the minimum. This is a more complicated situation, but it's a similar question. What total L and S come out from adding together? In this, for carbon, it would be for adding together the angular momenta of two electrons and distributed amongst various orbitals in the 2p subshell. All right, so the first question is which L and S values occur? Now, I should tell you that an LS value pair like this is called a multiplet. It's called a multiplet because those energy levels are only eigenstates of the electrostatic model. And when you take into account fine structure, you find that they're split. So that's the origin of the terminology multiplet, but that's what it means. We'll call them multiplets. These are the These are labels of the eigenstates of the electrostatic model. Okay. Then the next thing that you'd need to do would be to determine these coefficients that are in here so that you can actually construct these states as linear combinations of Slater determinants. And then you'd need to compute all the cross terms, all the terms, direct and cross terms of matrix elements of H1 with those Slater determinants in order to get this matrix. You only need the diagonal elements, as I said, but you'd have to do some computation of matrix elements to get those. Now, I'm not going to do that part tonight because I think it's too much for this course. We don't need to do it, but to understand that would be what you would do in order to do this calculation. All right. Finding matrix elements of distinct Slater determinants is an interesting problem. We may come back to it later. It's best handled by means of field theory, which is one reason why I'm not going to do it tonight. But in any case, let's just continue with somewhat of an outline of what we're planning to do here. So as I say, the problem is to determine the L and S values. Let's take the case of the 2p subshell as an example. Let's make a list of some elements here. Let's start with beryllium, which has the configuration 1s squared, 2s squared. Then boron, carbon, nitrogen, oxygen, fluorine, and neon. Did I do that right? There should be 1, 2, 3, 4, 5, 6, 7. There should be 7 of them because you have a 2p. There are no 2p electrons in beryllium. Boron has one single 2p. Carbon has 2 of them. Nitrogen has 3. Oxygen has 4. Fluorine has 5. And neon has 6. So you see beryllium consists of complete subshells, and so does neon. It's a noble gas, but in between you've got incomplete subshells. The 2p has got different filling factors from 0, 1, 2, 3, 4, 5, 6. That's what's going down here like this. Let's start with this. Probably the best place to start is with boron. Let's take that. Boron is has only a single electron in a 2p subshell. So enumerating the M sets is particularly easy. It's just the ML and MS values for a single electron in the 2p subshell. The ML can range from 1 down to -1, and MS ranges from 1/2 and a -1/2. So we get 1/2 and 1 -1/2. We get 0/2 and 0 -1/2. And we get -1 1/2 and -1 1/2. And there they are. There's 6 of them total, like this. And you may notice that's the same thing as the binomial coefficient 6, 1. The number of ways of putting, so 6 choose 1. You put one object in 6 slots. And these are the angular momentum and spin quantum numbers of the electrons. Now, the L quantum numbers of the electrons are all equal to 1 because it's all a p subshell. And the spin quantum numbers of the individual electrons are all equal to 1/2. And there's only 1 electron in there. And given the fact that the L and the S of complete subshells, which is the core here, is 0, all the angular momentum comes from the incomplete subshells, the partially filled ones. And so in the case of boron, the total angular momentum of the atom and the total spin of the atom is just given by that single electron in the 2p subshell. So therefore, the capital L, which is the angular momentum of the whole atom, is the same thing as lowercase l, and so is the capital S. Same as the lowercase s. It's L equals 1, S spin equals 1/2. This is denoted in the business by the code doublet P. It's really an LS value. An LS value is a multiplet. But multiplets have code like this. The doublet stands for the spin degeneracy, so it's 2s plus 1. The P is the usual code letters for orbital angular momentum, here capitalized to indicate the L value for the entire atom. So in our table here, beryllium has a multiplet, just one multiplet, which is a doublet P. Let me put it here as doublet P here. We'll make a table for beryllium. So that was easy. By the way, did I say beryllium? I meant boron. As far as beryllium is concerned, it doesn't have any electrons at all in the 2p subshell. So this is actually a singlet S. That's to say it's both L equals 0 and S equals 0. That's because complete subshells have total angular momentum of both orbital and spin are both equal to 0. So we've got two of the atoms taken care of like this. Now let's move on to carbon. Let's do that. Carbon has two electrons. Here's a simple way of finding out the multiplets that occur in carbon. We have two electrons with L1 equals L2 equals 1. They both have one L of 1, and S1 equals S2 equals a half. So if we combine the orbital angular momentum of the two electrons, it's 1 cross 1. That means we can get a total orbital angular momentum of either 0 or 1 or 2 using the rules for adding angular momenta. Likewise, for the spin, a half cross a half, as you know very well, gives you singlet plus triplet, which is a 0 plus a 1. Now then, so this is what happens when you just combine the orbital and spin angular momenta. However, the state has to be properly antisymmetrized. We know that when we combine the spins, we know that we know that the triplet state is symmetric under exchange, whereas the singlet state is antisymmetric. And if you did that problem involving the deuterium molecule, where we had a spin of 1, combining 1 cross 1, you know that when you combine 1 cross 1, you know that the total L equals 2 is symmetric, L equals 1 is antisymmetric, and L equals 1 is symmetric. The general rule is when you combine any two identical angular momenta, they have to be identical in order to talk about exchange. You combine two identical angular momenta, the maximum value of angular momentum that you can get is symmetric under exchange. And then it just alternates symmetric, antisymmetric, symmetric, going down to 0. That's the rule, which you can prove if you're motivated to do so. In any case, this is how it works in combining orbital and spin for two equivalent electrons like in carbon. But we know that the electron wave function has to be overall antisymmetric. So let's make a table here of L and S. So if we choose L equals to 2 here, that's symmetric, you see. That must be coupled with a spin 0, which is the antisymmetric part, to give overall antisymmetry. So this gives us what we call a singlet D. And by the way, the degeneracy of this is given by the total number of magnetic quantum numbers, which is 2L plus 1 times 2S plus 1. So for singlet D, that degeneracy is 1 times 5 is equal to 5. There's only one spin quantum number, but 5 L's. All right. Now, if the L is equal to 1, on the other hand, that's antisymmetric, so it has to be coupled with a spin symmetric state. So that's also spin equals 1. Well, that's what we call a triplet P. That means there's 3 spin states and 3 orbital states for a total of 9 states altogether, counting all the magnetic quantum numbers. Finally, if L is equal to 0, that's the last choice here, that's symmetric. That has to be coupled with a spin antisymmetric, which is a spin 0. And that gives us a singlet S, which is 1 cross 1. 1 times 1 is 1. That just gives us 1 state. So if we add up these numbers, 5 plus 9 plus 1 equals 15. And there you are. There's the degeneracy of the ground state in the central field approximation. So what we see is that 15-dimensional ground state of H0 in the central field approximation decomposes under the perturbation, or under the organization by the eigenstates of L squared and S squared, into 3 multiplets, which are characterized in the code. There's singlet D, triplet P, and singlet S. Let me put them up here. Singlet D, triplet P, and singlet S. There's 3 possible multiplets there. And when we turn on the perturbation, as I indicated, the energy shifts are going to depend on L and S, so it's going to give you 3 different levels of the carbon atom, and this is going to give us the exact quantum numbers of them. And the energies won't be exactly right, because we'll be doing perturbation theory. But the quantum numbers that we're assigning to these are exact and correct quantum numbers. All right, so that's how it works with carbon. Now, carbon has only 2 electrons, and this method that I showed you of coupling symmetric and antisymmetric only works in the case of 2 electrons. What I'd like to do now is to find my pen, which dropped. I guess I'll have to find it later. It's too much trouble now. Get a new pen. What I'd like to do now is to, let's see, what was I going to say next? Oh, yes. So what I'd like to do now is to show you a different method for computing the multiplets in carbon, which can be generalized to more than 2 particles, because this method cannot be. So let's do that. This is a graphical method. And to do the graphical method, I'm going to go back to our table of M sets for carbon, which is over here. We worked this out in the last lecture. Let me draw a vertical line here. Here's all 15 M sets for carbon. I'm going to create a couple of more columns. One is ML and the other one's MS, like this. All right. And ML, I'm just going to add up the magnetic quantum numbers for the 2 electrons. So for Slater determinant number 1, I hope you can see this, is 1 plus 1 gives me 2, and the total spin value is 0. Then I've got 4 1 zeros here for the 2 MLs. That's going to give me a total ML equals to 1, 4 of them. The spin values are a half, which is 1, half minus a half, which is 0, minus a half, which is 0, and minus a half, which is minus 1. Then I have 4 1 minus 1s, which add up to a total ML of 0. Put that in, and the spin values are just like we did a minute ago, 1 0 0 minus 1. Then we have ML MS equals to 0 for a total ML of 0. The spin values also add up to 0. Then we got 0 minus 1, actually 4 of them in a row. That gives me 4 minus 1s for capital ML. And the spin values go 1 0 0 minus 1 as before. And then we got minus 1 for a total of minus 2 for M sub L. And again, M sub F is 0. So just adding them up, then this gives us our columns here for total ML and MS. Now at this point, we proceed with the same kind of logic we used in constructing Clebsch-Gordan coefficients. Logic works like this. These Slater determinants are eigenstates of LZ and S sub Z with the quantum numbers given here. There's a table that lists them all. They're not in general eigenstates of L squared and S squared. Let's look at what we can call the doubly stretched state. That's to say, the doubly stretched state, the maximum value of M sub L is 2. And within the class of M sub L equals 2 values, let's pick the maximum M sub S, which in this table is only one state. That's the first Slater determinant. That's that 2 0 here. This Slater determinant is therefore an eigenstate. It's a non-degenerate eigenstate of L squared, of LZ and SZ with quantum numbers 2 and 0. And therefore, by our theorem that we talked about way back in the first semester of this first week of the first semester, if we have an operator that commutes with LZ and S sub Z, then this state is automatically an eigenstate of that operator. Actually, we have 2 such operators. They're L squared and S squared. They both commute with LZ and SZ. And since this state is non-degenerate, this Slater determinant must be an eigenstate of L squared and S squared by itself. The question is, however, what are the eigenvalues, or what are the quantum numbers? So the operators are L squared and S squared, and the quantum numbers I'm just calling L and S. So what are the values of L and S? What is the multiplet, in other words? Let's look at L first of all. L cannot be less than 2, because that would violate the rule that the M sub L would have to be less than or equal to L. So that won't work. Nor could L be greater than 2, because if it were, let's say the L were equal to 3, then in this state, then it would mean that it would be possible to apply a raising operator to get an M sub L equals to 3 state, the raising operator of orbital angular momentum. However, there are no ML equals 3 states in this list. And so therefore, this must be an L and S equals to, L is equal to 2. And by a similar logic, the S value has to equal to 0. That's to say, this is the tip of the iceberg, or the doubly stretched state of a multiplet with L value equal to 2 and S value equal to 0. Let me put a check by that, because that means this state, this Slater determinant, we now know what L and S multiplet it belongs to. Now then, this multiplet contains 5 times 1, which is 5 states, which are obtained by applying lowering operators to this doubly stretched state. You can't lower the M sub S because it's 0, but we can lower the L. We can change it down from 2 down to 1 0 minus 1 minus 2. Let's do that. If we lower it once, we get a 1 0 state. Well, here's a 1 0 Slater determinant. Let's check that off. Then lowering it again, we get a 0 0 state. Here's a 0 0 Slater determinant. Let's check that off. Lowering again, we get a minus 1 0. Here's one of those. Let's check that off. And lowering again, we get a -20, we check that off. So this gives us these 5 states which belong to that multiplet. Now I want to be clear about what I'm doing here. There actually are 2 Slater determinants, 3 and 4, both of which have 1 and 0. When I checked off the first one of these, I did not mean that if I apply a lowering operator to Slater determinant number 1, I get Slater determinant number 3. No, that's actually not what happens. What happens is I get a linear combination of Slater determinants 3 and 4. But the checking it off is a way of just counting dimensions. What it means is there's a 2-dimensional subspace in which the quantum numbers are ML and MS equals 1 and 0. And we have now taken up one of the dimensions of that 2-dimensional space. That's what that check means here. And similarly for these other checks. All right, now then, ignoring the ones we've removed already, let's now find the maximum ML and the maximum MS. Well, that's this 1, 1 here. This must correspond to an L equals 1 and an S equals 1. Oh, by the way, the 2, 0 is what in the code language would be called a singlet D. There's our singlet. Let me write it better so you can see it. It's a singlet D. That's the singlet D that we found earlier. Now then, the next multiplet that's emerging is the 1, 1, which is the triplet P. This is, of course, dimension 5, and the triplet P is dimension 9. So this is the doubly stretched state of the triplet P. Now we get to lower both the ML and the MS quantum numbers. Let's lower MS first. So we have a 1, 1, we lower MS, we get a 1, 0. Let's check off that. We lower it again, we get a 1, -1. There it is, check off that. And that's the end of it because L is equal to 1 now. But now we can, excuse me, because the S is equal to 1. But now we can lower the M sub L. Let's lower this to get a 0, 1, and then lower the M sub S. So 0, 1, here's 1. Then a 0, 0 lowering M sub S, and then a 0, -1 should be there. There's 1 right there. And then now let's lower the M sub L again to get a -1, 1, which is here, a -1, 0, and a -1, -1. There, I've just checked off nine more states, and these are what we get from this doubly stretched state by applying lowering operators in both spin and orbital. All right, what's left? The 0, 0 is left. It's the only thing left. That is an L equals 0 and a spin of 0 like that. We'll check that off. It has only one state. That's a singlet S, one state like this. And again, these numbers add up to 15. So the point of doing this, I'm sorry that there's spots in my screen that are obscuring this, but the point of doing this is to show you that this is a tabular method that gives the same answer that we had by just combining the angular momenta and constructing antisymmetric states. The advantage of doing this by the tabular method, however, is that it can be used for atoms that have in cases in which we have more than 2 electrons in an incomplete subshell. And so to illustrate that, now let's move on to the case of nitrogen. Let's do nitrogen here. So nitrogen has the configuration 1s squared, 2s squared, 2p cubed. It has 3 2p electrons. So therefore, the number of degenerate, the degeneracy of the ground state of the central field approximation is the 6 choose 3, which turns out to be 20. It's 20-fold degenerate. There are 20 Slater determinants. Now, we could construct a table just like this for nitrogen and list out all 20 M sets, but it turns out there's a shortcut that saves some work. And that is that when we're identifying multiplets, we always have non-negative values of the M sub L and M sub S because we're looking at the maxima. Once you find the maxima, you apply lowering operators, and then you get down to negative ones. But to identify the multiplets, we only need the ML and MS values, which are greater than or equal to 0. Now, in fact, in this table for carbon, I listed them all. But let's do it for nitrogen now, and let's just skip the ones for which either total ML or total MS is negative, and let's see what we get. So let's make another table now for nitrogen. So I'll have 1 here. So we have 3 MLs, ML1, ML2, ML3. We have MS1, MS2, and MS3. We're going to have MS3. We're eventually going to have a total ML and a total MS. We want those to be non-negative. All right, so let's do this. Let's set this table up. So for starters, let's start with the maximum value. That would be ML is 1, ML2 is ML1 is 1, ML2 is 1. And should we make ML3 equals to 1? Assign all 3 electrons to have ML equals plus 1? No, that won't work. The reason is that the spin values, assign 3 of them as well, and they can only take on values plus and minus a half. And if all 3 MLs are equal, there is no way to assign plus and minus a half MSs without making 2 of the MSs equal. And that means that 2 of the electron states will be equal to one another. And so by the Pauli principle, or if you like, the rules of determinants, the Slater determinant is 0. It's not an actual state. So we can't put a 1 here. We need to put a 0 there if we're going to list these ML numbers in descending order. Now then, what are the MS quantum numbers allowed? In the case of the ML quantum numbers are equal, the MS quantum numbers have to be 1/2 and minus a half. They can't be any other choice. We couldn't make the both MS numbers equal to one another because again, we'd have 2 electron states that are identical. So these 2 have to be distinct. And so one has to be a half and the other has to be minus a half. Moreover, I'm putting them in this order, the half first and the minus half second. If I did it in the reverse order, it would not be a new state. It would just be a rearrangement of the M sets, which doesn't give us a new state. Remember, it's only the occupied orbitals that count, not, it's only the list of occupied orbitals, not the order of the list. So in order to prevent duplications that way, I'm making these ML quantum numbers decrease, you see, going decreasing order. So on the other hand, the MS3, which corresponds to the ML3 equals 0, can take on either 1/2 or minus 1/2 without creating duplications. But the minus 1/2 would give us a negative value of total MS, so I'm going to omit that. All right, so that takes care of the 1, 1, 0. Let's move on then. 1, 1, minus 1 would be the next one in the list, and this is very similar. The first 2 are the same, so I have to have MS with a half and minus a half, and the MS3 has to be the plus a half like that. The next one down would be this, it would be 1, 0, 0. And again, this is where 2 MLs are equal and 1 is distinct. So the first one is a half and the second one is a half and minus a half. Second 2 are a half and minus a half. And the next one down, I have 1, 0, minus 1. Oh, this is nice, you see, because now we've got all 3 M sub Ls are distinct. And thus there are no constraints on the M sub S quantum numbers. All 8 possibilities could be listed here. So let's put the, or 4, 5, 6, 7, let's list this out. 1, 0, minus 1, 1, 0, minus 1, 1, 0, minus 1. In principle, there's 8 of these. I only listed 4. The reason I did is the following. Let's put some M sub S values in. Let's give all M sub S's a half, and then we'll allow one of them to be negative, either the last one, or the middle one, or the first one. And at this point, I can stop because if I allowed 2 M sub S's to be negative a half, then the total M sub S would be negative, and we don't need to consider that. All right, so that gives us 7 states. Is there an 8th state here? 1, 0, minus 1. What would the next one be? Well, it would be 0, 0, minus 1. You see, that's the next one down you could use, but that's not allowed because that would give me a negative M sub L. So in fact, out of the 20 Slater determinants for nitrogen, using the simplifying rule, we only need to list 7 of them. Here's what they are. Now let's identify multiplets. We need to add up the ML and MSs. So the ML in the first one is going to be 2, 2 in the next one. Oh, sorry, it's going to be 1 in the next one. Let's get it right. 1 plus 1 plus minus 1 is a 1. And the next one is a 1. And the next 4 are zeros. As far as the M sub S is concerned, we have a half for the first one, a half for the second one, a half for the third one, 3 halves for the fourth one, and then 1/2 for the remaining ones. And I fear this is getting over into the spots on my screen, and indeed it is. All right, let's identify multiplets. The maximum ML value is 2, maximum MS value there is 1/2. This is a multiplet which we call doublet D. Let me put it down here, doublet D. It's 2 times 5 states, which is equal to 10. If I lower the M sub L, I get, instead of 2 1/2, I get 1 1/2. So let me check off this first one. If I lower the m sub L, I get 1.5. So let me check off one of those. Lower it again, I get 0.5. I'll check off one of those, and the others are negative. As far as the m sub S, I can't lower that without reaching negative values. All right. Now proceeding down to finding the maximum ml value of what's left, I've got 1 and 1/2. This has got to be a doublet P. So I'll put that down here in the list, doublet P. That's a 2 times 3, which is a total of 6 states. So lowering the doublet, the 1.5 I'll check. That's the 1.5 I'll check. Lowering the m sub L, I get a 0.5. Take care of that, and that's all I get from lowering things. Looking now at what's left, I've got the 0.3 halves. This is now the maximum value of m sub L, and within that value, here's the maximum value of m sub S. So it's 0.3 halves. This is what you call a quartet S. Quartet means spin equals 3 halves. So let me check that. Now here we can't lower m sub L, but we can lower m sub S, and if we do, we get 0.1/2, and takes care of that state down there. And now you see all the states are checked. So what we've got is quartet S here. 4 times 1 equals 4 is the degeneracy of that. Now add this up, 10 plus 6 plus 4 is 20. There's your binomial coefficient. So this is the tabular method for nitrogen. And you see it tells us that this gives us the multiplets which occur in the ground state of nitrogen. So here they are, doublet D, doublet P, and quartet S. Let me go back to my table. Where did I have my table? Yeah, it's right here. Here's the table. For nitrogen, it's doublet D, doublet P, and quartet S. Okay? The table here, constructing. All right, now then. What about oxygen with four electrons in the 2p shell? Oxygen fills up 4 of the slots, and it leaves 2 holes behind. Those are empty slots. What you find if you do this business long enough is you find that holes work the same as electrons insofar as determining multiplets are concerned. It's easy enough to show that. But what it means is that if I go through the tabular method again, or any method for finding the multiplets in the case of oxygen, what I'll end up with is the same ones as in carbon, because of the equivalence of electrons in holes. So for oxygen, we get, just copying the carbon results, we have singlet D, triplet P, and singlet S for oxygen. For fluorine now has only a single electron, a single hole. It's got 5 electrons in one hole, but the one hole behaves the same as a single electron, so it's got the same multiplets as boron, which is doublet P. And finally, neon is a singlet S, as all the noble gases, all complete subshells are singlet S. Their total L equals 0 and total S equals 0. They're totally rotationally invariant under both orbital and spin rotations, you see. And that's an exact statement, because these are the exact quantum numbers of the level. Even if we don't know the energy, only approximately, these quantum numbers are exact. All right, anyway, these then are we've now created a table of multiplets for the filling of the 2p subshell. All right. Now,
Professor.
Yes.
Can I ask a question about about the tabular method for nitrogen?
Yeah.
I think I just have a misunderstanding.
So you can see it here.
Understand what's going on, right? So for the 101 case, you considered the case where all the MS were positive 1/2, and then the permutations of where 1 was negative 1/2.
The 1, 0, minus 1, you mean?
Yeah. Sorry.
1, 0, minus 1. I allowed all 3 spins to be distinct.
Right.
Because
okay. So I guess you are accounting for like also the if it was 1/2, negative 1/2, and negative 1/2, that they kind of get absorbed. They're not different than, they don't say anything new other than what this is saying here.
I'm not sure what you're asking, but the 1, 0, minus 1, these ML values are all distinct. Yeah. So this means that the 3 orbitals that the electrons are going into are guaranteed to be distinct no matter what spin quantum numbers I assign.
Right. Okay.
So there's actually 8 different ways of assigning spin quantum numbers. but
Right.
only 4 of them are going to give us a non-negative value of m sub s, really a positive value.
Okay,
That's
okay.
why I only listed 4 of them.
Yeah, perfect. That sounds good. I just wanted to make sure that there were other states, but yeah, this is.
Yeah, okay. It's actually kind of fun to do 1 or 2 of these, see how it works out.
Yeah, thank you.
You know, when you start this, you'd say this is really intimidating. I know how to combine 2 angular momenta, you know, like 1 cross 3 halves, because we learned that. But now what I've got to do is combine angular momenta of multiple electrons and spins, and combine, you know, both of them combined together. And I've got to take into account the anti-symmetrization. So it sounds like a horrendous task, but actually, if you just do this, it's really quite simple to do it. Okay, so those are the multiplets then. All right. Now then, as I explained, this gives us the energy shifts, which depend on L and S. And these are the matrix elements, L, S, ML, and MS, sandwiched around H1. And these then are the, and we now know the degeneracies of these states as well. These then are the multiplets. Okay, the total energy of the E0, add E0 to that. The E0 is the sum of those pseudo eigenvalues, perhaps you'll recall, as the sum on lambda, the epsilon lambdas. And adding the ELS corrects for this and takes into account the effects of spin and so on. What I've done so far doesn't tell us anything about the ordering of these levels L and S. It doesn't tell us which L and S are. Particularly, if you're interested in the ground state, you want to know which one is the lowest multiplet. There have been a set of people who've done calculations of this type and developed a set of empirical rules which are used for determining what is the ground state. These are known as Hund's rules, and I'll now tell you about them. I'll tell you about 2 of them anyway. The first Hund's rule is the following: is that the lowest multiplet, meaning lowest in energy, has the highest S, highest spin. So what that means is, if we go to our table of the 2p shell here. Now, by the way, in this table for beryllium, boron, fluorine, and neon, there is only 1 multiplet, so that's automatically the ground state. So the real issue is the 3 middle ones, carbon, nitrogen, and oxygen. Which one of these multiplets is the ground state? Well, Hund's rule number 1 says the one with the maximum spin. So for carbon, that's the triplet P. Let me use the red ink to circle it. For carbon, that's the triplet P state, because that's the triplet is the highest spin. The same thing is true for oxygen, because it has the same multiplets. As far as nitrogen is concerned, it'll be the quartet S, you see, is the ground state. Right. Now then, what happens if I have 2 multiplets that have the same highest value of S? That didn't happen here, but it happens in other problems. So I'll give you now, this is Hund's rule number 2. So if 2 multiplets have the same maximum value of S, then the lowest one has the highest L, highest orbital angular momentum. There's a third Hund's rule, which I'm going to postpone for a minute because we don't need it right now. Let me just make some comments about these Hund's rules. These are semi-empirical. I mean, they partly come out by doing lots of calculations and looking at the answers. However, especially Hund's rule number 1 has an important physical interpretation. It's the same interpretation that we've seen a number of times in multi-electron systems, which is that the higher the spin value, the more symmetric the spin part of the wave function, and therefore the more anti-symmetric the spatial part of the wave function, and therefore the electrons are kept further apart, and therefore the Coulomb energy is lowered. And that's the essential reason why Hund's rule number 1 works. Now, if you look in the literature, you'll find explanations for Hund's rule number 2. And I've never been myself convinced that they're correct, and so I won't tell you what they are. Let's just say this is an empirical rule, but there it is. And Hund's rule number 3 we'll come back to in a minute. All right, so Hund's rules then give us the orderings. So for Yes.
Do Hund's rules apply for more than just the ground state? So if we're looking at,
No, they're really only talking about the ground state.
okay,
So for example, in the case of carbon, we'd find that the triplet P would be the ground state. Hund's rules don't tell us what the ordering of the other two states are, but they happen to be the following. The next one is a triplet, singlet D, and the highest one is the singlet S. You can look these up in tables. People have assembled, both experimental and theoretical data. The NIST website has got a tool that you can interact with, where you can enter in, your units for the energies and so on, and type in the configurations and so on. You would look. Well, anyway, if you want to have some fun, go to that website and look at some of those energy levels. In the case of carbon, I actually created a plot and a set of notes of the low-lying levels of carbon, not just these three, but ones coming from other configurations as well. And it's interesting to look at because you can see the layout of the low-lying energy levels of carbon. Okay, so anyway, so that's has to do with the ordering of the energy levels. Now, that's as much as I want to say about finding the eigenstates of H0 plus H1, which, as I explained, is the electrostatic model for the multi-electron atom. However, I'd like to add some comments about what happens when we include the fine structure effects, what we called H2. The functional form for H2, which I gave, is really somewhat schematic, but it gives you the right idea. We get the sum over the electrons I equals 1 to n of a function of the radius of the electron I times the L dot I orbital or spin orbit term for the given electron I. This is in fact one of the contributions to the fine structure. There are other contributions as well, which I'm omitting because I don't want to go into the details. But you can see this is basically a sum of spin orbit terms of the type which occurred in hydrogen, and they also occur in multi-electron atoms as well, for the same reason. But there's other terms also. There's spin other orbit. There's spin interactions. There's kinetic energy corrections. There's a lot of other stuff as well. This is just a sampling right here. In any case, let's consider what's involved in now finding the energy shifts due to H2. So, by the way, in the case of carbon, what we see is that the 15-dimensional ground space of eigenspace of the central field approximation is split. We can think of it, this is splitting, you see, from the central field approximation with 15 states here. It's split like this into 1 state there, into 5 states there, and into 9 states there, like that. So what the H2 is going to do, potentially anyway, is split these substates even further. And in accordance with the general methods of degenerate perturbation theory, you can see we need to think about degenerate perturbation theory in analyzing this problem. For example, to find out what happens to the triplet P ground state of ground multiplet of carbon when we include fine structure, we have a degenerate state. It's degenerate perturbation theory. You're going to get a 9x9 matrix. So what would that matrix look like? Well, it could look like this: LS, ML, and MS, sandwiched around H2. Now the L and the S are the labels of the multiplet, which is the triplet P. So they're the same on the two sides of the matrix elements. But the ML and MS represent the basis inside the 9-dimensional degenerate eigenspace of what is now the unperturbed Hamiltonian is H0 plus H1. So we need to put primes on them. At least you need to put primes on it to create now a 9x9 matrix. Well, in this course, our philosophy is never diagonalize matrices if you don't have to. What can we do to avoid diagonalizing a 9x9 matrix? The solution really ought to be obvious based on everything we've done in this course so far, is we need to do a change of basis inside the 9-dimensional space to create an eigenbasis of operators, create an eigenbasis whose quantum numbers are quantum numbers of operators that commute with H2. Now, ML and MS correspond to the operators LZ and S sub Z, which of course are components of the vector operators L vector and S vector, which generate orbital rotations, purely orbital rotations, and purely spin rotations separately. So as far as L vector is concerned, you can see it's going to rotate all orbital variables, including the L sub i's of the individual electrons. It'll generate rotations that rotate the L sub i's. However, it won't change the S sub i's. And therefore, H2 is not invariant under rotations generated by L, nor for the same reason is it invariant under rotations generated by S. Do you see the power of thinking about rotations as to say group elements rather than calculating commutators to find out what commutes with something? You can see this very clearly without ever calculating a commutator. You can see that this does not commute with any of the components of S vector, in particular not with S sub Z. And so therefore this matrix with ML and MS quantum numbers on here is going to be a full matrix. The solution, therefore, is to switch over to a basis, which are eigenstates of operators which do commute with the perturbation H2. Well, what operators do that? The answer is obvious. It involves the total angular momentum J, which is L plus S of the entire atom, orbital plus spin. Notice this is the total J of all electrons, orbital plus spin, because L and S are the total for orbital and spin separately. Now this does commute with L dot S because the J operator generates rotations of all vector operators. And if you rotate Li and Si both by the same rotation, the dot product is invariant. So we need to switch over to eigenstates not of J vector because it's three non-commuting operators, but rather to J squared and J sub Z. And we do this, of course, just by using Clebsch-Gordon coefficients. We're really just adding L and S to create total J. And so let's create new states that look like this. The L and S labels, the multiple labels are the same, but the ML and MS are now replaced by J and M sub J. M sub J, let me write it this way. And this is equal to a sum on ML and MS of the LS, ML, and MS states, which themselves are linear combinations of Slater determinants, times Clebsch-Gordon coefficients, which is what that is. That's just a standard Clebsch-Gordon coefficient. And now we get these operators. And now let's look at the matrix elements, LS, J, MJ, sandwiched around H2 because we're taking H2 as a perturbation now, LS, J, and MJ. And now we don't need primes in the L and S because that identifies, as I said earlier, identifies the unperturbed eigenstate. And we don't need primes on the J and MJ either because J squared and JZ commute with H2. So we just need to compute the diagonal matrix elements, and those will be the energy shifts. And what will they depend on? They'll depend on L and S, which is let's write it this way, it's delta E sub L and S. They'll depend on L and S, which is the multiple in question. They'll depend on J because there's no reason why they don't, but they won't depend on MJ because of rotational invariance in the Wigner-Eckhart theorem. So we get energy shifts delta E, delta LS, delta LSJ, splitting these energy levels. So, for example, to go back to carbon, what that means is the ground state, the triplet P, is going to split into levels according to the J values. Well, what are the J values? The spin is equal to 1 and the orbital angular momentum is equal to 1. If we combine 1 cross 1, we get 0, 1, or 2. For the singlet D, there's only a single value of J, which is J is equal to 2 because that's the L part. The spin is 0, so it's only the orbital part contributes. And here for the singlet S, the J is equal to 0. But the ground state's got 3 J values. All right. So the different J values are indicated in standard spectroscopic notation by a subscript. For example, we have a triplet P2 is what the J equals 2 level would be how it would be represented in spectroscopic notation. These others only have 1 J value. So the first one is singlet S0. The second one is a singlet D2. If you wrote those in the full spectroscopic notation. All right, now the question then arises, which of these J values is the ground state? And this leads to Hund's rule number 3. I think rather than trying to write it out, I'll just tell you how it works. It works like this: is that if the shell is less than half full, so for example, in the case of carbon, we have 6 slots and 2 electrons. So that's less than half full, because half full would be three electrons. If the shell is less than half full, then the lowest J is also the lowest energy. So I didn't make room for this here, but if I were to draw my energy diagram for carbon, this of course is not to scale or anything, but in the central field approximation, we had 15-fold degeneracy. Then we've got the triplet P here. We've got the singlet D and the singlet S. This is 9, 5, and 1. This is H0. This is H0 plus H1. And when I turn on H2, we get fine structure, and the triplet P splits into triplet P0, triplet P1, and triplet P2, like this. And this just becomes singlet D2, and this becomes singlet S0. All right. So if you go look this up on the website, the NIST website, you'll be able to see this. This is fine structure, so it's bigger than in hydrogen because carbon has Z equals 6, but it's still not all that big compared to the separation between the levels. It's definitely fine structure, and this is what you'll see there. Okay. There's another part to Hund's rule number 3, which says that if the subshell is more than half filled, as for example, in the case of oxygen, then it's the maximum J has the minimum energy. So the oxygen diagram would look the same as the carbon diagram, except these J values would be reversed. The ground state is a triplet P, J equals 2, triplet P2 state, like that. And that's Hund's rule number 2, Hund's rule number 3. Okay, that's all I want to say about the structure of multi-electron atoms. I think this is a minimum of what you need to understand to have a semi-quantitative, mostly qualitative understanding what the low-level eigenstates are like and where their quantum numbers come from. And that's all I want to say about it. Are there any questions about it before I move on to other topics? No questions, okay. So that's all I want to say about multi-electron atoms. It'll be all I'll be saying about many-body fermion physics for a while. I may come back to it later in the course. I'm right now engaged in some juggling of topics, thinking about what I want to cover in the rest of the course. There's been some unhappiness from, not necessarily from students, about too much relativistic quantum mechanics, so I'm considering cutting some of that out and putting more non-relativistic stuff. In any case, this is enough for atoms for now. I'd like to embark on in the time I have left tonight, about 10 minutes. I'd like to embark on the subject of time-dependent perturbation theory to give you just a bare introduction to it, which is our next major topic. So time-dependent perturbation theory concerns Hamiltonians that you can write in perturbation form as H0 plus H1, and we allow H1 to depend on time. It doesn't have to depend on time, and in fact, most of the applications that we'll consider it doesn't, but it is allowed. So, for example, if you want to know what a light wave does to an atom, then the H0 could be the atom Hamiltonian, and the H1 is the effects of the light wave. And it being a light wave, it's time dependent. That's a typical problem. In contrast to bound state perturbation theory, which we did last semester, where the system has bound states and we're interested in finding the shifts in the energies and in the eigenfunctions, in time-dependent perturbation theory, we're usually interested in different sorts of questions. What we're really interested in usually is what you call transition amplitudes and transition probabilities. The idea is roughly this: is that you have some states we call the initial and final states, we write as F here for a final state and an initial state like this. And you put the time evolution operator for the whole system, the U is the time evolution operator for H in the middle. The initial and final states are just names we attach to it, but typically they are eigenstates of the unperturbed Hamiltonian. So this is called a transition amplitude, and you can think of it pictorially, or at least there's words that go along with it, which say that this is the probability of finding the system in the final state F at the final time, given that it was in the initial state I at the initial time. The U of t just evolves it forward in time. Scalar product gives you the transition amplitude. The probability is the square of this. So this is what's called a transition amplitude. And so computing transition amplitudes is one of the main goals of time-dependent perturbation theory. Now the perturbation H1 of t, which may depend on time, in fact, it may depend on time in such a way that it is localized in time. H1 is really an operator, and so I can't really graph it, but I'm going to do it anyway. If you imagine that the H1 is turned on over some limited period of time like this, between two bounding times t0 and t1, then what that means is the system is governed by the unperturbed Hamiltonian before t0 and also after t1, but that the perturbation, which was on during this limited period of time, is going to introduce some changes. A nice example of this was the impulse that was delivered to our iron atom on a spring. Remember, we did that last semester. We also did it with, I think, in a homework problem with the Landau problem, where the impulse was delivered by the emission of a photon. So there was a momentum transfer. That was an example in which the time-dependent perturbation took place over an infinitesimal period of time. So it was represented by a delta function, kind of a limit of this. But you may recall that we had our oscillators in some state in before the perturbation was turned on. And after the perturbation is turned on, we've got some state psi, which is the sum on let's call it states m of coefficients c sub m times m. In other words, it becomes a linear common, even if it's an eigenstate of H0 before the perturbation is turned on, afterwards it's going to be a linear combination. And these c sub m's are the transition amplitudes. In fact, it might be better to write them as c sub n goes to m, the way that I've done it here, because it gives you the amplitude to make a transition from the initial state to the final state. And of course, the system might remain in the initial state. That was part of the issue with the Mossbauer effect. Okay, so this is an example of what the type of problem that could be handled by time-dependent perturbation theory, in which the notion of the transition amplitude is very clear. There are other problems that are much more subtle, but they have some similar characteristics. The one that's of most interest is the scattering problem. This is something I don't think I want to draw pictures. I'm just going to use words, so try to use your imagination. I'm thinking of a scattering problem where we have potential scattering. So there's a potential energy which is localized in space. And what we do is we stand off at a distance and we send wave packets at the scatterer. The scattering potential dies off with distance. That's the normal assumption in scattering theory. Otherwise, it's not really scattering theory. It's localized, in other words. So at a large distance where we're launching these wave packets, the potential is negligible. And the evolution of those wave packets, at least initially, is governed by the free particle Hamiltonian. So they're governed by an H0, which is a free particle Hamiltonian for large negative times, let's say, beginning times. Now, as the wave packet evolves and moves towards a scatterer, eventually it starts to overlap with the potential. And as a result, those scattered waves will start to radiate outwards from the potential. And how this plays out depends on how big the wave packet is compared to the potential, if you can assign a size to it. If the wave packet is much bigger than the potential, then some of the wave, a lot of the wave is just going to pass right by it, but the parts that hit it dead on will create a scattered wave. All right, so I hope you can visualize that. Now, after a while, what's going to happen is the wave packet is essentially going to pass the potential. Some parts of it are going to more or less pass it without being deflected much, and others are going to generate a scattered wave that'll go off in all directions. But if you wait long enough, those waves will leave the neighborhood of the potential energy. In other words, it won't be a wave packet anymore in the sense of being localized, because you've got waves going on all directions, but it will leave the vicinity of the potential. And so what will happen if you wait long enough into the future is that once again, the the state will be governed by the free particle Hamiltonian. So as far as that goes, it has similarities with this picture I drew here in that there's only a limited amount of time, perhaps a long time now, not a short one, but there's only a limited amount of time during which the potential is active, not because it was switched on and off, but because of the dynamics of the wave packet. As far as what the wave packet sees, it's only effective during a certain amount of time. And so time-dependent perturbation theory can be used to analyze those problems as well. That's a tricky analysis because one has to talk about fully time-dependent evolution, one has to talk about wave packets. Free particle solutions don't have any bound eigenstates. So you're dealing with a continuous spectrum. There's all kinds of issues that come up. But nevertheless, the basic idea, I hope, is clear. And one is interested then in the transitions between the states that existed at large negative times and the states that exist at large positive times. And this leads into the subject of the S matrix, which I'll say a little more about in maybe not tonight, maybe I will tonight. I don't know, depends on time, but maybe more substantially later in the semester. All right, but this is just some background on transition amplitudes and why they are interesting. Okay. So transition amplitudes are one of the main objects of interest in time-dependent perturbation theory. Now, by the way, most of the stuff we're going to be doing for the rest of the semester will involve scattering and decay processes, and time-dependent perturbation theory is the main method for dealing with them. So this is the beginning of what we'll be doing for the rest of the semester. We have two Hamiltonians here. We've got the unperturbed one and the total Hamiltonian. It's convenient to introduce time evolution operators for both of them. If I do it for the unperturbed system, it's the differential equation is IH bar du0 dt is equal to H0 times U0. And if I do it for the full one, it's IH bar du dt is equal to H times U, where H is the same thing as H0 plus H1 times U. So the idea is that U0 is the time evolution operator for H0, unperturbed system, and U is the time evolution operator for the full system. So the U is going to be hard to calculate. We're going to need perturbation methods for doing that. But we're assuming that H0 is solvable, and therefore we can solve this equation, and we know what U0 is. Formally, U0 is given by e to the minus I t H0 over H bar. You can solve it in that form. And sometimes that's a useful expression for evolving things under H0. H1 has no there's no similar expression for H1 there's no similar expression for U because H1 is allowed to depend on time here. All right. Now, the time-dependent perturbation theory is conveniently developed in terms of what's called the interaction picture. I'll remind you from last semester about the Heisenberg picture and the Schrödinger picture. The Heisenberg picture is one in which the state vectors evolve and the operators don't. Let me say it right. The Schrödinger picture is one in which the state vectors evolve and the operators don't. The Heisenberg picture is the opposite. The state vectors don't evolve and the operators do, according to the Heisenberg equations of motion. The difference between them is that in the Heisenberg picture, the time evolution has been stripped away, which is why the state vectors don't evolve anymore. In fact, the state vectors in the Heisenberg picture are the same as the state vector in the Schrödinger picture at the initial time. It's just that they don't evolve, so they stay that same state vector forever. Now, in time-dependent perturbation theory, it's convenient to use the interaction picture. This differs, it's kind of an intermediate version of this. This differs from the Heisenberg picture in that we don't try to strip off the total time evolution, which we're going to have a hard time knowing what that is anyway. Instead, we strip off just the part that's due to H0, which is a part we have under control because we can solve H0, that's what we're assuming. So here's how we'll set this up. I'll write the state vector in the interaction picture as psi sub I of t, where I stands for interaction. And the definition of this is that this is U0 of t dagger applied to the Schrödinger state at time t, where the S stands for Schrödinger. So this is what I'm saying is you strip off the time evolution due to the unperturbed system, giving us the interaction picture. We can also talk about operators in the interaction picture. This is defined as U0 of t dagger times the operator in a Schrodinger picture times U0 of t. In other words, it's the Schrodinger operator conjugated by the time evolution of the unperturbed system. This makes A of I acquire a time dependence even if A sub s doesn't. Usually A sub s does not, sometimes it does. In any case, this is the definition of the interaction picture. I won't be talking about the Heisenberg picture in dealing with time-dependent perturbation theory. We'll only use the Schrodinger and interaction picture. The Schrodinger picture will be the default if I don't put subscripts on something that'll be understood to be in the Schrodinger picture. Okay, we're exactly out of time, so I won't run over even 1 second, except to ask if there's any questions about this. I know we're just getting started on this. We'll fill it in next time. Any questions about this?
Could you clarify what the difference is between the Heisenberg picture and the interaction picture?
Yeah, in the Heisenberg picture, to go from the Schrodinger picture to the Heisenberg picture, you remove all of the time dependence. So you'd use this U of t here, this U operator, which is the total time evolution operator. To go from the Schrodinger picture to the interaction picture, we just strip off the part that's due to the unperturbed Hamiltonian.
I see. Okay.
Here's one reason why you want to do that. If I go back to the scattering problem, which I described in words, so it's kind of hand waving, but you recall that at large negative and large positive times, the state is evolving according to the free particle Hamiltonian. It's not because the perturbation's been switched off, it's just because geographically it's somewhere else. So these wave packets or these states, these quantum states, don't overlap with the potential, not in the large time limit. And so they evolve according to the free particle Hamiltonian. Now, in some sense, what you'd like to do is to define the transition of the system as taking you from the asymptotic state as t goes to minus infinity, into the asymptotic state as t goes to plus infinity. That's really describing the scattering process. But the problem is, because they evolve according to the unperturbed Hamiltonian, they never actually approach a limit. In fact, the wave functions as t goes to infinity, they just move out to infinite distance and disperse themselves, and there is no limit. So to get a limit, what you need to do is to strip off the evolution from the free particle Hamiltonian at both large positive and large negative times. And I'll say some words about that in my next lecture, because that's the basic concept of the S matrix. In any case, the interaction picture does that for you, you see.
I see. Got it. Thank you.
Got it. Yeah. All right. Any other questions?
I have a question, but it's on the fine structure perturbation.
Yeah. Yes.
So you were talking about splitting in carbon, and so you said that the 3p splits 3 times. Is it just 3 because it's 3p? Like would a doublet split twice, or?
No, it's the triplet. You call it triplet p. The triplet refers to the spin. It's this weird way of saying the spin equals to 1, s equals 1. The 3 is 2s plus 1. It's the degeneracy of the spin state. So anyway, triplet p means s equals 1 and L equals 1.
Mm-hmm.
So the reason we get the reason we get 3 outcomes is because if you combine L equals 1 with S equals 1, you get, by the rules of addition of angular momenta, you get J equals 0, 1, or 2.
Oh, okay.
Those are the 3 outcomes. If we had a triplet D, you get a different results.
Okay. I see.
Okay.
Thank you.
And those other 2 states were singlet states. So the spin was 0. So the J was just equal to the L value. So
Right.
So the singlet D, for example, became J equals 2.
Gotcha.
Yeah. Okay.
Cool. Thank you.
All right. Any other questions? All right. Good. These are good questions. All right. Yeah. So if you have any more complicated questions that you come up with, this came up today. Somebody sent me one by email. Feel free to send me something by an email. If it's important enough, I'll bring it up in lecture, or else we'll do it in office hours. If it's really minor, I'll just send you a reply. But but these are good questions, so bring them up. I think they're educational for everyone. Okay, so I think we're done. And screen share. Pause recording.